Okay, so welcome back to our course. This is the seventh class. It's about nuclear reactions. So, as we said way back, we talked about nuclear reactions as interactions between nuclei. It's a bit more complicated than this. Some people define it as transmutation induced by radiation. It's a bit more complicated than that too. But essentially, nuclear reactions are events in which two particles they interact via the strong force, right? The nuclear strong force. And so, what happens in a nuclear reaction? You have just like a chemical reaction. Chemical reaction, you have an atom or a molecule that exchanges electrons with another atom or molecule, and so on, right? So here is essentially the same. So, for instance, you may have boron 10 interacting with a neutron and producing a lithium 7 and an alpha particle, right? Essentially, you can have calcium 48, for instance, interact with a neutron and absorb this neutron, so it becomes calcium 49, still calcium, one more neutron, and you have to produce a gamma ray. It's mandatory, right? For conservation purposes, you must have this gamma ray. You may have, for instance, carbon 12 interacting with a proton, producing carbon 11 and a deuteron. And here there's an important note. For all nuclei, we used the regular notation, right? Carbon 11, carbon 12, calcium 48, calcium 49, and so on. But this is not true for hydrogen. For hydrogen, because it's the most common element on the universe, and because of tradition too. So we use so we say proton instead of hydrogen 1. We say deuteron instead of hydrogen 2, and the symbol is a D. And we say triton or tritium, the symbol is a T for hydrogen 3. Okay, so this here is hydrogen 2. So if you have this one, you can understand like, okay, we have a proton that passes through a carbon 12 nucleus and steals one electron from it. So now one neutron from it. So now the proton becomes a deuteron because it now has an extra neutron, and the extra neutron is missing here, so this is carbon 11, not 12. And you also have, for instance, a gamma ray that will collide with an indium target, removing a neutron from the indium target, leaving it so it was indium 113, becomes one indium 112, and you have now a neutron just away from it. One very, very important thing. When we talk about decays, we have the alpha decay, which is simple, things conserve everything, but we have the beta decays, the three ones, beta plus, beta minus, and also electron capture, in which protons become neutrons and vice versa. This does not happen in nuclear reactions. Beta decays are ruled by the weak force, the nuclear weak force, and the nuclear weak force plays no part in nuclear reactions. So you will never have proton becoming neutron, neutron becoming proton in nuclear reactions, right? Because of that, the number of protons is conserved and the number of neutrons is conserved. So just look here, boron has 5 protons and 5 neutrons, this one. So it absorbs a neutron, now we have 5 protons and 6 neutrons. Lithium has 3 protons, alpha has 2 protons, the 5 protons we had. Lithium 7 has 4 neutrons, alpha has 2 neutrons, 6 neutrons again. Same goes if you go for every single reaction. So in nuclear reactions, you have, if you sum up all protons you had before, you will have all of them later. If you sum all the neutrons you had before, they will all be here. They are just rearranged, okay? For simplicity, we define a target and a projectile. So for simplicity, we say, okay, this neutron, it collided with a boron particle, boron nucleus. The neutron collided with the calcium nucleus. The proton collided. We always think of the lighter particle as colliding with the other. And I say this is for simplicity because if we inverse the reaction, we have a proton target and we inside with carbon-12 nuclei, the reaction will be exactly the same. The products will be exactly the same, nothing will change. So we only, to simplify things, define the lighter particle as the target, as the beam, and the heavier particle as the target. Same thing here, we say we are left with these nuclei and these are the particles, just for simplicity. Well, the notation. So now we have, for instance, nitrogen 14 with a helium beam inciding on it, or as I said, could be the opposite. So if we had 14 plus 4, we have 18, 7 plus 2, we have 9 protons, so this is fluorine 18. With a twist, these brackets here, they mean this guy here is produced in a very, very excited state. It's not regular fluorine 18, right? It won't decay with the half-life of fluorine 18. It's very, very high excited state, and this will decay on its way to this one. In this case, oxygen 17 plus a proton. And if you see, 14 plus 4, 18. 17 plus 1, still 18. 7 plus 2, 9. 8 plus 1, still 9. Okay? And now we write this down just for simplification, to shorten things. We say that an alpha particle, and we had a nitrogen 14 target, an alpha particle incided on it, a proton left it, and we were left with oxygen 17 on the target. Okay, and this becomes the name of the reaction. We often say that we had nitrogen 14 and an alpha P reaction left it with oxygen 17. Same thing goes for the other ones in the previous page. For instance, we have boron 10, we have an N-alpha reaction, so meaning a neutron comes in, an alpha comes out, and you're left with lithium 7. Calcium 48, an N-gamma reaction, meaning a neutron comes in, gamma comes out, and you're left with calcium 49. Carbon 12, proton comes in, deuteron comes out, remembering deuteron is hydrogen 2, and we're left with carbon 11, and so on. Okay? So, what are the basic laws that rule a nuclear reaction? Well, the number of masses. These four here are laws that are essential to any process in physics. The number of masses conserved. This is true for all kinds. If you remember, even when we were talking beta decays, protons becoming neutrons and vice versa, the number of mass was conserved, because a neutron becoming a proton, still one number of mass, right? Charge is conserved, which is true always. So that's why when we said in a beta decay you have a beta plus, you have a positive particle leaving the nucleus, you must have one less positive charge inside the nucleus, so that charge is conserved. So in this case, a proton becomes a neutron, you have one less charge in the nucleus, and you have a positive charge leaving the premises. So yes, charge is always conserved. Energy is always conserved, remembering that mass is energy and energy is mass. So when we do energy conservation, we have to take mass into consideration. Angular and linear momenta are always conserved too. This is the essential laws for everything. And there's an extra law that's not written here, but I already told you on the previous slide. As nuclear reactions only involve the nuclear strong force, protons are conserved and neutrons are conserved. So the number of protons you had before the reaction will be the same you have after the reaction. Number of neutrons you have before the reaction will be the same you have after the reaction. They will be only misplaced. They will exchange places, okay? Bohr in 1936, trying to describe how a nuclear reaction happened, and he was talking about, we'll talk about later, but he was talking about what we call a complete nuclear reaction. or fusion evaporation reaction is the complete name. First of all, you form a compound nucleus in a highly excited state. So these two join up and form this compound nucleus in a highly excited state. And then these highly excited states will decay, forming whatever it will form, regardless of how it was formed. It doesn't matter what happened up to here. This part is separate from this part. This part will only depend on who this guy is and what kind of energy do we have here. Okay, this is a complete reaction or fusion evaporation reaction. So just quickly, fusion evaporation, because you say, okay, these guys are fused into a larger nucleus, and this nucleus evaporates a particle and becomes another nucleus. So okay, nuclear reactions. Before we had a target and a particle, and after we had another particle and another target. So for conservation of energy, things get very simple, because as we don't have protons becoming neutrons and vice versa, electrons are not a problem. The number of electrons you had before is the same you have after, and everything is okay. So conservation of energy is essentially the mass of the initial particles minus the mass of the final particles, right? The mass of all this plus this, minus the mass of all this, right? So there's two cases. You may either appear, if these guys are heavier than these guys, then you have Q is positive, right? And this reaction releases energy, right? If these guys are lighter, meaning some mass disappeared during the reaction, meaning, okay, this is an exothermal reaction. You produce energy by it. If these guys here are lighter than these guys here, right, then the mass of the final particles will be greater than the initial particles. The Q will be negative, and you have an endothermal reaction, a reaction that absorbs energy. For decays, you cannot have a decay with Q smaller than 0, okay, because you don't have where to get this energy from. In reactions, we can, because you have to remember this particle is not, in a decay you have just a stopped particle here, right? In rest. In a nuclear reaction, this particle can have high kinetic energy, and so this energy enters in the balance too. So if it has an energy that's large enough so that the reaction can occur, even if a Q that's smaller than 0, yes, it can, because this particle can bring this energy, right? Because of the kinetic energy of the particle. But if we apply conservation of momentum, the numbers are not here. It's an easy calculation, much similar to what we did with the decays back there, to see how much of the energy goes where for the one or the other. If we apply that too, we will find out that the minimum energy here's energy, right? Forget it. For a reaction, which we call the threshold for a reaction, the energy of the projectile has to not only be greater than Q in value, but there's this small calculation also. So it has to be, because it's easy to understand, right? It has not only to have the energy enough energy to start the reaction, right, which is Q, minus Q in the case, but as conservation of momentum is important, the particles won't be still after the reaction, right? We had a stopped particle here, we had an ongoing particle here, we had some momentum, we have to conserve momentum after. So you have to have some recoil of the particles later. So if we do some math, you see that the minimum energy for a reaction to happen is minus Q times this. Meaning that if Q is positive, right, this energy will be negative, meaning any energy is enough for right? So exothermal energies can happen with particles of any energy. There's no limit, no threshold. But if Q is negative, then this becomes a positive number, and the energy of the kinetic energy of the projectile has to be greater than a certain amount. We call it threshold. So one example here, the reaction we posted before, right? Nitrogen 14, helium, proton, oxygen 18. Just doing the math, we have the Q of the reaction is minus 0.932 mega electron volts. So this is an endothermal reaction, right? These two guys here are heavier. If we sum up these two masses, they are greater than these ones. So mass is created. For that to happen, we have to bring energy to the table. It consumes energy, and so the helium particle here has a minimum energy below which this reaction cannot happen. So we do the math here, just as it was there, and we found out that we need 1.2 mega electron volts energy for this. If the alpha particles has less than 1.2 mega electron volts of kinetic energy, this reaction will not happen. Cannot happen because there's just not enough energy. Okay? So once again, remembering we were talking about before about roundings, right? In roundings in those calculations. The same thing that goes for the case happens again here. If we all use all decimal digits, I mean, this is what we find in a table, all these decimal digits here, we discover that the Q of this reaction is minus 1.19. But if I round the masses to only 3 digits, we come to 0.932. Quite a difference, right? Almost 20% difference. So, once again, in my class, if you're doing my exercises or the tests that I propose, round to the number of digits I give to you. Sometimes it will be 3 decimal digits, sometimes it will be 4, and it's not random. Sometimes I need 4 digits to prove my point. That's only that. But if you do anything for serious, you have to do that for your work or something, you do need to use, I know it sounds a lot, but you have to use all digits because this will make a big difference. You see, in this case, almost 20%. Okay? So keep that in mind. In my tests, in this course, use the number of digits I give you. In real life, use all digits you can. So let's just talk briefly about the types of reactions we have, right? Not all of them, but some that are more important. One very important one that happens a lot is elastic scattering, meaning you have a particle that will collide with the nucleus, just change direction, it will displace the nucleus a bit, change direction, but leave with the same energy. This is called elastic scattering, right? We all know it from other examples here and there. So in this case, we would write it like this, right? Almost obvious. So you have A coming in, you have A coming out, you had X before, you had X later. As the incident particle is equal to the outgoing particle and the nucleus is equal to the other one, Q is 0, right? This is very common, happens a lot, especially with neutrons. We'll go to that in a moment, right? So that's essentially the most important thing. Okay, this is a very common reaction, but it only, in fact, scatters particles. You don't produce radioactive nuclei, you don't change the nature of radiation, you don't do much. Now, there's also inelastic scattering. What is inelastic scattering? You have a particle that will inside on a nucleus, it will leave the nucleus in an excited state, and you have an identical particle leaving with another energy. So this is written like this, right? So you had X, you had particle A coming in, a particle A coming out, but X was left on an excited state. The incident particle is equal to the outgoing particle, meaning it's a scattering. The particle is just scattered by the nucleus. But now the nucleus is left on an excited state. As the nucleus will be excited, it will absorb part of the energy, right? It's required, because if you want to excite this guy, you have to give him energy, so this is an endothermic reaction. It consumes energy. Some of the kinetic energy of this guy will go to excitation energy on this guy. This is also very common, and it's, of course, if this guy is left on an excited state, on a second stage, at some point, this guy will emit back this as a gamma radiation, right? So, this is an example. You have a neutron scattering on oxygen, leaving the oxygen 16 on an excited state, right? And this is how we write it. Other types of reactions. For instance, we have alpha N. You have beryllium-9. It interacts with an alpha particle producing a neutron and a carbon-12 nucleus. Just as a curiosity, this was the reaction that Chadwick used to discover the neutron, right? He had alpha particles inside on a beryllium plate, and he noticed he was producing this kind of strange radiation here. That was the neutron. You can have, for instance, alpha P. You can have an alpha particle coming in, a proton coming out, and then, right, all the rest, you just do it's much similar to doing balance in a chemical equation, right? If you know what you had here, you know the incident particle and the outgoing particle, you can calculate simply what's left. You can have, for instance, a deuterium or a hydrogen 2, where a gamma comes in and removes the neutron from it, and you have hydrogen 1. So this is a gamma N reaction, and so forth. Lots of different reactions here. Possibly the most common ones, the ones that especially we here use most, are N gamma reactions, where a nucleus essentially absorbs a neutron, emits a gamma just for conservation of momentum, and so we had stable aluminum, and all of a sudden this became radioactive aluminum, right? Aluminum 27 is stable, aluminum 28 is radioactive and decays with a 2.5 minute half-life. You can have, for instance, the one I showed before, an alpha, where boron absorbs a neutron and becomes a lithium-7, and essentially everything can happen provided you have enough energy, because usually more complicated reactions will require more, and will have a smaller Q or more negative Q, and will require more energy to happen. That's essentially how things happen. And so let's recycle this. We all saw this one on the first class in fact, right? So this is the binding energy per nucleon. I showed you this on the nuclear models of class 2. So now we can take a look back at this and say, okay, I told you at that time that if we got two lighter nuclei and put them together, we should release a lot of energy, right? And that if we got a heavy nucleus and broke it in two, we should also release some amount of energy. As I told you at that point, this here, when we join two nuclei to produce a heavier one, we call it nuclear fusion, because we're we're fusing things, right? You have two nuclei that will become one, and then as they fuse together, we release energy. And when we break a big nucleus in smaller pieces, we call it nuclear fission, because it fissionates It divides in two. So, talking about nuclear fusion. As I talked when we were talking about nuclear reactions, I said that the complete nuclear reaction is also called fusion evaporation. But for energy production purposes, when we talk nuclear fusion, we are usually talking about three main reactions, right? When we have hydrogen 3 or tritium interacting with a deuterium, you produce a neutron and a helium 4, right? This one has 17.6 mega electron volts Q positive, meaning every time this reaction happens, you release almost 18 mega electron volts of energy. That's a lot. But it depends on the existence of hydrogen 3, which is rare. You have also here hydrogen 2, which is deuterons, which are more common when they interact with other deuterons. This is the fact for these two reactions. You can have two things happening. You can have a neutron leaving and you're left with helium 3, which is a stable nucleus of helium, a stable isotope of helium, right? And you produce 3.27 mega electron volts. Or when a deuteron interacts with another deuteron, you can produce a proton and a tritium, right, with 4 mega electron volts of Q. All of these are positive. This is much more positive than the others, but all of them can produce energy. More than that, this one produces tritium, which then can be used here. So we can use this reaction to start to produce a lot of hydrogen 3, tritium, and then this reaction starts to happen too, consequentially, right? So that's the idea. When we say nuclear fusion, we say we want to produce energy by nuclear fusion. We're talking about these three reactions, and usually this cycle where deuterons start to produce energy and produce tritium, and after a while this reaction kicks in, and when this reaction kicks in, then we're talking a completely different amount of energy, right? And what about nuclear fission? Nuclear fission happens with heavy nuclei, right? As I told you, you have to be on the down slope of the binding energy per nucleon figure. They are very energetic. The Qs we're talking now are around 200 mega electron volts. Why? Because when you see the slope, you say, oh, that's not that much, but you have too many nuclei, a lot of them. So even if the binding energy per nuclei is not that different, when we multiply it by the number of nuclei of nuclides that are interacting there, we're talking about very much. So we're talking 200 mega electron volts, 200 something, a little bit. And these are very energetic, and they result in 2 or more fragments of different sizes, plus a few, usually 2 to 3 neutrons, right? This is a very, very energetic reaction, meaning that each time it happens, you will have a slightly different outcome, right? So one time you may have, say here we're talking about uranium-235. One time you may have the fission happening, and you're left with something here like strontium something, and something here that's cesium something, and 3 neutrons. The other time it may be xenon here instead of cesium, and here maybe another thing. And on one time it may produce cesium 137, on the other one 134, and so. And sometimes you have 3 neutrons, sometimes you have 4 neutrons, sometimes you have only 2 neutrons. Also, sometimes this may break in 3 different pieces. Sometimes you may produce alpha particles here too. So this being having too much energy involved here makes many different pathways possible, right? So when we're not discussing a specific reaction, right, we use the notation like this: 235 uranium and fission. This means that statistically we know what will happen, we don't know which individual reaction will be. And this may occur spontaneously in californium-252 and other very heavy nuclei. But the most common one was californium-252. And an important thing to note is you produce a lot of neutrons. We'll talk about this when we talk applications, right? So this is essentially the idea of fission, right? And just a quick glimpse, why is fission so easy to tame? While we cannot do fusion reactors now, we can do fission reactors. We'll talk about this in the first applications class. But essentially, you have a neutron, it gets a nucleus, you have a fission, and you have, 2 to 3 neutrons that may start new fissions that will produce other nuclei, and will produce more 2 to 3 neutrons, and you see all of a sudden 1 neutron became 3, became 9, and of course a lot of energy is released, and a lot of neutrons too, right? And when fission happens, remember I told you, statistically we can know what the outcome will probably be after 1,000, 1 million or something fissions. But we can not know each individual fission reactant which will be. Well, here's an idea we call fission yield is the percentage, the number of times a given nucleus is produced, in this case in percent, right? In fission. So here, let's take for instance here uranium-236, which is uranium-235 plus 1 neutron, right? So you see it will produce something with mass between 90 and 105, right? So a typical example in this region is strontium-90, and it's very important for us nucleus because it has 30 years half-life. So it will be a problem because most of these fragments, they are very, very short-lived. Some of them are, I don't know, averagely short-lived, but some of them, they end up being living for 30, 80, 90 years. So this is the big problem here, strontium-90. And here on the up part, we are around 130 to 145, right? For instance, two famous guys that appear on this side. We have cesium-137, also important because of the 30 years half-life, and also iodine-131, which is very important because it's a gas, and every time you have an incident on a nuclear power plant where radiation is released to the environment, you will see iodine-131 there, right? If you saw Chernobyl, the series Chernobyl, you saw that the accident was detected in Sweden a few days later because of an iodine radioactive cloud, iodine-138, which is produced by the fission directly, right? So just a glimpse of it. And you see, depending on which is the nucleus that is being fissioned, you change the fragments a bit. Something that's important, you may produce the same nucleus by several different reactions, depending on the target and sometimes on what is your, depending on the target and depending also on what you have. You have a neutron beam, okay, you will produce things using neutrons. If you have, so you have all these ways here to produce sodium-24 using neutrons. If you have a gamma ray source, then you have to do one of these, right? So There's several reactions. Each of these reactions will have a different Q. Some of them will be exothermal, some of them will be endothermal. They will end up in sodium 24. Right? The important thing is, you can check me, but in every of these one of these cases, the number of protons and the number of neutrons is conserved. Okay? And also, as I showed you before, we can use this. Remember, I told you this here, that we had hydrogen 2, which is deuterons with deuterons, and we had two possible reactions, right? Okay, same thing happens for every possibility. Every time you have the same projectile and target, you may produce a lot of different reactions. Remember, each pathway here has its own Q, because the products are different, so the Q is different. Some of them will be exothermal, some of them will be endothermal, some of them will require more energy, some of them will require less energy, but all of them are possible, right? So, just to give you an idea, for instance, for very low energies, usually, with very, very few exceptions, only reactions with neutrons can happen. Because neutrons have no charge, so they can approach the nucleus in stealth mode. They are not detected until they are inside the... See, you know that guy that crashes parties, that goes into parties without knowing anyone there, and all of a sudden he's inside the party as if he knew everyone. Yeah, that's the neutron. Because because if we have a charged particle, it will be positive, trying to enter a nucleus. When it gets too close, you have repulsion, you have electrical repulsion, so you have to overcome this. And to overcome this, you need kinetic energy. Now, the neutron doesn't need that because it doesn't have charge. It doesn't feel the repulsion. So for very, very low energies, essentially only the neutron can have interactions at that kind of energy. When you increase the energy a bit, you see some simple reactions happening. So low energy, essentially N gamma, but you may have also some N alpha reactions and that. You increase the energy, and all of a sudden you start to have other reactions possible too. But very simple reactions, right? Proton can interact with producing a neutron or a gamma or an alpha. A deuteron can produce. Okay, very simple things, but things start to get more tricky. When we go from 500 kilo electron volts is half a mega electron volt. So now changing scale to mega electron volts, we start to have more complicated reactions, right? You may have, for instance, a deuteron, and here you may say, okay, you have a deuteron here, you have a proton and a neutron here. So it's the same. It's not the same because the deuteron is the proton and the neutron in a bound state. When we say PN, it means they are not. So in this case, the deuteron was split in two pieces, in its two basic pieces, after interacting with the nucleus. And when we increase energy, you see much more complicated reactions starting to happen. So, as a rule of thumb, low energy means simple reactions, and as you increase energy, you start to have more complicated reactions happening. Right? But when we talk about reactions, we may want to calculate, okay, but what's the probability that this reaction will happen? Because now we know that they happen, we know some of them will require the projectile to have a certain energy, but which is the probability that this reaction will occur? This is given by the cross-section. Cross-section is essentially a measure of the reaction probability, right? As we borrowed all the formulas from classical mechanics, cross-section has units of area, right? So if you take a look in classical mechanics, when you think of cross-section of a collision, you think meter squared or centimeter squared. But now, as the nucleus is very, very smaller than that, then the unit we use is the barn, right? Because it comes from a joke. Some scientists said that to collide two atom nuclei would be like finding a knee stack on a barn, right? And of course, this just when physicists have this weird sense of humor from time to time, and the unit is the barn. And the barn is essentially thinking of the sizes of the nuclei, which are essentially 10 to minus 12 centimeters. So we have 10 to the minus 24 square centimeters, right? So this is essentially the unit we use. It's a unit of area, right? But very, very small areas indeed. And if we think about, okay, how do we define this? You have this number of particles per second inciding over sample, and the sample has a density of ρ, right? The probability of interaction is given by this equation, where ρ is the density of the medium of the target, right? dx is just a differential depth, meaning it's just a very, very small delta. As I told you before, think of these d's as very, very small deltas from this. Remember delta x, delta t is the speed and all that, right? So then we get this deltas each smaller and smaller and smaller. We get to this minor d's here. But this is what we call a differential equation. It's saying that the amount of particles from the flux that will be absorbed is proportional to the density of the target, which makes sense, right? Because the more dense the target is, the more nuclei you have to collide with. It has to do with the depth, of course, because the deeper you go, more particles you have to interact with. And there's this sigma here. The sigma here, as you see, is something like a probability. So if I have this number of nuclei per particles per second inciding in this target here, the reaction will have to do with this guy here. And one important thing to notice is directly proportional, meaning that if sigma is 1 or if sigma is 2, the number of reactions will double. If I double this, I double the number of reactions. If I quadruple this, I quadruple the number of reactions for the same target, right? So if we solve all this up, we end up with this one here, right? This equation. And essentially the number of product nuclei after the if we remember we had a reaction, we want to see how many nuclei of the product were left on the sample after irradiation, and it will be given by the flux, of course, because if we double the number of particles we inside, we will have double the reactions, right? It's proportional to the density. Once again, if I have double the number of nuclei in the target, I have double the reactions. To the thickness, same reason. To the time, because the longer I irradiate, more nuclei I will produce, and it's directly proportional to the cross-section too. So once again, the important thing about the cross-section is it's a measure of the probability that this number of atoms of particles will produce something in this target for this time. So if I have two different reactions, one has 10 times greater cross-section in that situation, it will happen 10 times more, right? If it's 100 times, it's 100 times more. If it's double, you have double the reactions, okay? That's the important thing about the cross-section. There's other important things too. the cross sections varies with the energy of the projectile. Well, you have already touched on this before without saying it, because if there are reactions where the particle cannot start the reaction unless it has some energy, remember I talked about the threshold of energy for reactions, then of course it's a function of the energy. If I told you that some reactions are more probable at higher energy and others at lower energies, I already implied this, right? So now I'm explicitly saying the cross-section changes with the energy of the projectile. And it doesn't change in a simple way. Sometimes you increase the energy, you reduce the probability. Sometimes you increase the energy, you increase the probability. Sometimes you increase the energy, it increases up to a point, then falls. Okay? One thing that's important, as I said before, the higher the energy, the greater the number of channels. Channels are each pathway of reaction, right? So I have, for higher energies, we have more possible reactions. So the higher the energy, the greater is the dispersion of what you can have happening there. And once again, just reinforcing that the reaction rate, or meaning the number of reactions that happen per second, is directly proportional to the cross section. Okay? So here, just some ideas of how are these cross sections. This is a famous N-alpha reaction for boron. So you have this, as I told you, this is a neutron, so it can happen for very, very low energy. See that here we're talking about log and base 10 logarithm of the energy. So here is milli electron volts and so forth. You have a very high cross section, which falls down until it reaches a higher energy where it gets complicated. For most nuclei, in reactions with slow neutrons, we have this, we call it the 1/v law. It's law, not really a law, it's just a trend. Meaning that for most of them, the cross-section just follows an inverse relation with the velocity of the neutron, right? The faster the neutron, the lowest the cross-section. But no, not all cross-sections are so simple. So here I'm talking about several different cross-sections. And there's one important thing too, because sometimes they think, okay, because the barn is a cross-section unit that has that size, 10 to the minus 24 centimeters squared, because of the size of the nucleus, then we say, okay, it has something to do with the size of the nucleus, right? Yes, but not. So let's just see one thing, right? Here we have, in light blue here, this is the probability, this is the cross-section for the capture in boron 11, right? And in green, the cross-section for the capture in boron 10. And you see, oh, boron 10 is smaller, but the cross-section is bigger. And it's much bigger for an alpha reaction. And on the other side, for boron 11, it's an endothermal reaction, so it has a threshold. It only happens above something. So you see, although the idea of the nuclear size and the classical view of the cross-section are useful, the real cross-section doesn't depend really on the size, but on the strength of the interaction of that particle with that nucleus, right? And this has to do, now just taking a quick hint on what we said before about nuclear models, this has to do with the states available for that particle in that nucleus. So if we take a look, for instance, for gadolinium, and then we have a wild party going on. We have, for instance, gadolinium 157 has a huge cross-section, while 160 has a very small cross-section. And you come up to a certain point where all kinds of crazy things happen, right? Not really. If you take a look, it's just what we call resonances. We can see them better maybe here, right? So spikes on the cross section. What are these spikes? For some reason the neutron has exactly the energy of a vacant shell on the target nucleus, right? So it's there, and then all of a sudden it discovers it fits perfectly on that nucleus, and then the interaction probability goes up 1 or 2 orders of magnitude. But then you have just a bit more energy. You don't have the perfect energy anymore. That's not for you anymore, and you go away, right? So these are what we call resonances. They are very common on neutron capture reactions. Here we have another idea, just to show you. We're talking about how size is not that relevant. So we have inelastic scattering in lead. It's very low. Elastic scattering in lead will be very low too. And then all of a sudden you see elastic scattering in hydrogen, which is small, but you see it's very likely all over this is for neutrons, right? You see neutrons tend to do elastic scattering with hydrogen a lot. This will be important for things we will discuss later. And here another example, you have a proton, now not a neutron anymore, so things get a bit smoother when we're not talking neutrons. So we have copper 63 and we're just throwing protons on it, right? And there's all these kinds of reactions that can happen. In lower energies you have the PN reaction, meaning okay, you will be forming zinc 63. As you increase energy, you see, as I told you, at very low energies this reaction doesn't happen, and then probability increases up to a point close to 10 MeV, and then starts to drop quickly, and all of a sudden this reaction is more relevant, the PN. Here, right, where you produce copper 62. Peaking, and you see the probability of this reaction just goes down very quickly, and now you have much more likely until 25 MeV. This one is much more likely, and then it starts to drop too, and you start to have this reaction dominating, which is the P2 and this here, right? So you see, I guess there's some mistake here. Okay, forget it. But the important thing is just to check this. Okay, we have the cross section. It depends sharply on the energy, and in the case of these reactions, you see, as you increase the energy, you start to get other reactions dominant, and they are getting weirder and weirder as things go for higher energies, right? And as you see here, you have a bump. So you have all kinds of different trends happening when you increase energy. But the important thing to remember is if the reaction is the strongest at this energy, doesn't mean it will be the strongest at any other energy, right? Here are more examples. For instance, gold 197, this cross section for neutrons, and you see here very complicated things happening here, right? It's resonances at low energy. They are for, and you see that this is for NP. No, this is for N gamma reaction, right? And then the light green here is for NP, which is only happens at higher energies. And then for even higher energies, the N2N start to happen a lot. This is one of those reactions I told you we can use to produce energy, the fusion reactions, a deuteron with a deuteron. And here are both of them, right? In blue is where you produce helium-3, and in green is where you produce okay, I'm lost here, but anyway, it's both you produce helium-3, whatever. It's just showing you, okay, you have cross sections can have all kinds of shapes. And this is a true example. We have a particle accelerator in the Physics Institute. If you ever noticed, there's a very tall building here, just below the IPENG, a very tall building with that has the symbol of the Physics Institute on top, and it has no windows. That's a particle accelerator. The building has this form because you have the accelerator is vertical, right? So there we can accelerate heavy ions and collide them with whatever we want. So essentially what we had there, we wanted to produce some nucleus, and we're trying to see, so we do calculations using models. This is one of the importance of models. We wanted to know essentially what reactions we would produce to know, okay, we want to produce, in that case, we want a nickel 61, okay? So which is the best energy to produce? So we have a target of vanadium 51 and a beam of oxygen 17. And we start to look the best energy. And you see, if I use 50 mega electron volt energy, I will produce more zinc 64 than everything else. We'll produce a bit of the rest and no nickel 60 because there's not enough energy here. If I increase the energy, things start to change, and as we wanted nickel 61, we tuned the beam to approximately 65 mega electron volts, and this would be good enough for us, right? So you see, you change the energy of the particle, you change the particles you produce, right? Another important thing, several times when you do, especially, well, any nuclear reaction, in fact, nuclear reactions, they tend to leave the matter radioactive because you're messing with the nucleus, you're changing the nucleus to another state, to another nucleus, and many times you will turn a nucleus into a radioactive nucleus. And then once again, it's almost like those things we showed you when we were talking secular equilibrium. If we start to irradiate some sample, right, just like in secular equilibrium, we have production and we have decay happening. So in the very beginning, it's almost a straight line. It's almost as if we're only producing, there's nothing there to decay, and as time goes on, decay starts to take place. And if you see, if we irradiate something for more than 5 half-lives, we don't produce much activity at all. We start, in the very beginning, we have a very steep curve, meaning it's almost like if this here was proportional to the time of irradiation, and then after a while, this is not even close to proportional to the time of irradiation anymore, and you start going on. So when your irradiation time is of the same order of magnitude as your half-life, there's a limit to how much you can produce. So this is very important when we're talking about, for instance, producing radioisotopes for medicine or something. You have a limit on how long you can irradiate things, because start to enter in an equilibrium phase where you irradiate longer, you just burn more target, and the activity you produce is still the same, right? So that's all I had to talk about activation, and so on reactions, in fact. So we see up to now we understood what's the nucleus, we understood what's radiation and how decays happen, and now we talked about how we can produce or use radiation to produce other nuclides, right? You can think of reactions almost like an induced decay. You use a particle to provoke a change on the target. Now, what we have left to do is talk a bit about, okay, how does radiation interact with matter? right? Because now we know how to produce radioactive things, how radiation works, and all this. Now we have to understand how radiation interacts with matter, being either targets us or anything. And that's what we'll start to talk about next class. Bye bye. See you later.